Welcome to the second part of this introduction. Here I will show you something more advanced regarding data handling and basic data management. So first, let's start with an exercise. You should now know how to handle data with basic R functions. So I will ask you to import the cars data in the ANT data in the data folder. Using the car data, then you should select only cars whose length is less than 450, select cars whose weight is more than 1100, then select cars that comply with both above conditions. Using the data set in 3, so the one with only cars selected by these two conditions, select only the column corresponding to the price of these cars, and then calculate the mean of such prices using the function callMeans. So what does it, one difficulty, you should remember to load the packages before actually attempting to importing the dataset. And the rest you should be able to do that with what you learned from the first part. And in a moment we will get the solution. So first thing first, you can create a new script, for example, if you want, or open the older script and keep editing that. But let's call it my second script. I create a txt file and I rename it as an R file. That's the easiest way to create an R script. So it asks me, would you like to change the file extension? Yes, and I have my R script. I open it, my second script, and then RStudio was already open, so I close RStudio, I open RStudio again by double-clicking on my empty script. So let's do this. Let's load the package pacman. I typically put this string before, so if there is no package pacman already installed, install it. And then I also say require pacman, so if it got installed, then load it. And then I use the function pload to load the packages that we need to read data. If you remember, that would be heaven, and then for this CSS file, and then reader. If you don't remember, it's okay, you just go here to import dataset, you import. Well, the car data are an SAV file, so you go to data cars.sav. It got imported, and you see here library haven. So now, if you don't remember that the package was haven, that's okay. You read it here, cancel. You copy paste the code. You put the code to haven here. The view is not very important anymore, so load the data. Packages. Then let's import the ANT data. It was a textual file, so go here, browse data, ant.csv, and it gets visualized correctly. So you copy the code, cancel here, paste the code, remove the code to the package loading, which is here, and then remove the code to view. Go here, run it, you get your data. You save the script. Then the first part of the exercise is good. Import the cars and the ANT data. Then using the cars data, select only cars whose length is less than 450. So what can you do? Cars. You remember you can select data in a data frame if it was a matrix, so rows and columns. You want only the rows, so the cars, which are the observations here, only the cars whose length is smaller than 450. So the length is in variable length. We do cars length smaller than 450, and that's the first part. So let's call it exercise about data management. Okay. Exercise about data management. Then I wanted you to select cars whose weight is more than 1100. So let's do this. Cars weight. I select the variable weight in cars, and I select only those larger than 1100. So this will be the first data. It's 14 cars whose length is more than 450 and 17 who weigh more than 1100. Then I wanted to select cars that comply with both of the above conditions. So it's just I copy this line and then I combine the two conditions here using the AND symbol, and I have only 7 cars which comply with both conditions. Now I wanted you to select only the price of these cars. So let's copy paste this. And how do we select a column? Well, you could use the number corresponding to the column, like 1, 2, 3, 4, 5, 6, 7, 8, 9. That would work, but it's not very good because if you change the position of the columns, then everything gets, the code doesn't work anymore. So it's better to address in general columns by name. So we only select the name of the column of interest, price, here. And here we get our data. And then the last would be to use, what was that, call means to calculate the mean of those prices. Call means. So here it is. The mean price of the cars that have lengths more than 450 and weight larger than 1100 is this 25,000 something euros. Well, you see, albeit this works nicely, one thing that I don't like about this way of handling data, I mean, this is the way of handling data using only basic R, without using packages that help in handling data. The thing that I don't like about it is that the expressions become very quickly extremely long. For example, you notice that when you want to select rows, for example, you have to remember to put the data frame from which you're taking the variable, even though often it is obvious that you are using a variable that is inside the same data frame you want to select rows from. Well, similarly, when you select the columns, you need to remember to put those as a textual, because this is the name of a variable in the dataset, so you need to remember the inverted commas. And then all these calls become very long. I mean, it's typically you end up writing a very long code into the same line. So maybe you are wondering, is there a simpler way to achieve this? Let's say this script, and the answer is fortunately yes. The reason why, however, I taught you how to select rows and columns of a data frame in basic R is because what I'm about to show you works like 90% of the time for things that you need to do. It doesn't work 100% of the times. There are things that you cannot do with the way I'm about to show you. For example, you cannot assign values to a variable using what I'm about to show you. So you have to know basic R, but you can use Dplyr, which is a package, to handle data in a more elegant way. So you end up coding a code that is more understandable. So let's see. Dplyr is a package. Let's first load it. To load it, we add it to our code to reload Dplyr. Here it is. So we re-execute this line and we have Dplyr loaded in our environment. Then, which functions are particularly useful in Dplyr? Well, this function, percent larger than percent, is sort of a pipe function that is shooting the output of what is before this command as the first argument of what comes next. It seems complicated, but let's just use it so that you can see what I mean. So here you are applying the function callMeans, and its first argument is this dataset. Wouldn't it be easier if you, for example, you can apply, I don't know, other function outside callMeans, open parentheses, etc. It is cleaner, the programming, if you do this. Simply this. So what you're saying is this thing that is before the pipeline command goes as the first argument of this. So this writing and this writing are equivalent. Here, the output is the same. But here, your code is a little bit cleaner. So you first visualize the operation made on the dataset car, and then you clearly visualize that you are applying call means on that. I don't know, you can then apply other functions, I don't know, square root. If you apply that here, using another pipeline command, you get the square root of the value before. If you want to apply it here, you have to write another function here, on the top of that. So this results in a line of code that gets longer and longer. This results in several lines of code that are indicate what happens next. And I find this command extremely useful in many, many occasions. So, then the select function allows you selecting variables based on their name in a data frame. All of this applies, except of this function that you can apply generally to every object, this function here applies to data frames. So the select function allows you to select variables based on their names. The summarize function allows you to condense multiple variables to a single value. So to have a summary, for example, a mean, a standard deviation, etc. Group by is used in conjunction with summarize to obtain summaries separated by different groups of data. We will see that in more detail in a few slides. Filter, well, select allows you to select variables, so columns. Filter allows you to select cases based on their values. Mutate allows you to add new variables that are functions of existing variables. And we won't see much of arrange and rename, but they allow you to reorder cases and rename the variables. Let's start with select command. Well, the first thing is, I originally put this syntax, but it's better to remove it and to just put the call to Dplyr inside the call to pload. So you load Dplyr using pload. And then let's, for example, select only the column length, baggage size, weight, and horsepower in select. Let's check it out. So first, maybe you just keep cars, the visualization of cars here. So the columns, model, length, baggage size, weight, if I remember correctly. Length, baggage size, weight, or power. This one, length, baggage size, weight, or power. Select cars. Which columns do we want to select? Weight, baggage size. I don't remember the names. Those I put names, cars here. Length was length. Length, baggage size, weight, horsepower. And that's it. I get a reduced dataset with only those columns. Since those columns are in a sequence here, so are ordered in this exact order, I can also use a shorthand, like the columns between length and horsepower, using the column syntax that we typically can only use when we create vectors, and we get the same result. You can also, I don't know, select only between the columns between length and weight. I can select the column between length and weight, and then let's check the price. And here it is, length, baggage, weight, and price. So I can select columns as I want. I can also change the variable names in this process. So for example, the columns HP is for horsepower. I can change its name to horsepower equal to HP, and I get a new data frame which includes the columns that I want in the order that I want, and it renames the column horsepower HP to horsepower. Notice that this does not change at all the content of the data frame cars. If we want, we can create a new dataset, cars2, and assign it this value. Then if we go to our environment, we have a new data frame that has only the columns that we want. But the only calling the command select, etc., does not interfere with the existing data. That's the rule that is generally valid in R. Okay. So you can use filter for selecting only some observations. For example, you can only filter on only cars with the airbag. So the airbag variable, if I remember correctly, is oh, I opened the wrong. So the airbag variable should be 1 if the airbag is included and 0 if the airbag is not included in the car. So we want only to select the cars with the airbag. So now we are not selecting variables, but we are selecting observations, so rows. We can use the command filter. So let's comment this code so that we can remember what we did. So select variables, select cases or filter cases. Select only cars with the airbag. So cars, let's do this. Filter, we specify the data set we want to filter from, and then we see airbag equal to 1. Remember, the double equal is to specify whether double equal symbol is for comparing values. So if you do this, you will get the correct output. So you only have variables with the airbag. If you do this without the double equal symbol, you will get an error. And it also tells, did you mean A equal to 1? In general, if you get errors, before panicking, you just read the content. If you read the content of these error messages, this one is very, very clear. So you can also combine select and filtering and the pipeline symbol. So combine, select, and filter with, for example, I want to select only cars, only the columns airbag. I want to select the price, horsepower, and I want to filter cases whose, I don't know, price is smaller than 20,000. Okay. And it gives me an error, of course, because the column horsepower doesn't exist. It's called HP. Now I get the results. So these are only the columns that I asked and only the rows that I asked. So only the cars whose price is smaller than this value. You can also add conditions. For example, airbag is present, for example. Here, we only have 3 cars which fulfill these conditions, and we see the columns that we request. Some things that are typically result in errors. Well, when you use the pipeline symbol, this is the first argument of this function. So this is actually essentially the same as writing, this. But you see how this command is much clearer than this one, because here you have function nested in function. So let's stick to this one. Then you don't have to specify cars again if you use the pipeline comment, because the first argument is actually already specified here. That's the typical source of mistakes when you use the pipeline symbol the first time. Then, okay. Now I want you to repeat the exercise we did above, this time using Dplyr. So there was a thing that was not anymore necessary. So what I'm asking you to do is, using Dplyr, selecting only cars whose length is lower than 450, select only cars whose weight is larger than 1100, etc., like you did the first time. But this time using Dplyr. And here comes the solution, so stop the video, try yourself. The solution is, first you filter cases, then you combine the 2 conditions in the same filter command, then you also select the column price out of that, and then you use the pipe command again and you compute the mean of such prices using column means. As you did before, this time you use the command filter, select, and pipeline symbol. Another exercise, compute the correlation matrix among the variables length, bagger size, weight, and horsepower. The correlation matrix can be computed with the command cor. So if you go to the help file of core, you see all the options, but essentially if you give a data frame to core, it computes the correlation of the variables you give as input. And here comes the solution. Here you select in cars the columns that you want, and then you can either put core on top of this data frame, so include this data frame as the argument of core, or better using the pipeline symbol and select the data first and compute the correlation later. So I told you that the function summarize allows you to obtain a new data set including the summary statistic you like. How does that work? Well, summarize takes as input the name of the data set you want to summarize, and then you can define variables as summaries of existing variables. For example, the mean, length, the mean of price, etc., etc. Let's try that together in our studio. So, for example, we can do summary cars. We can have mean length. We say is the mean of the variable length. Mean price is the mean of variable price. You can also, I don't know, median length is the median of variable length. Standard deviation of length is the standard deviation of variable length, etc., etc. I'm sorry, it's summarize, the function summarize. I always make this mistake. So if I run that, I have this. So the mean of the length, the mean of the price, the median of the length, the standard deviation of the length, etc., etc. You can add anything you want here. But the summarize function is not very useful if you use it like that. I mean, you get the summaries. You could get the summaries also by typing, I don't know, mean of cars dollar length, and you get the same value here. This is not rounded, it's only represented shortly, but the true number behind this is this. But it's useful if you use it in conjunction with group by. So what is group by? Group by takes a data frame and it applies the summary separately by different levels of other variables. For example, let's try it together. I take group by, let's put a comment here. So summaries statistics with summarize. This we can remove it. Group summary statistics by group with group by and summarize. Now we can do group by cars by, for example, the presence of airbag. This does not do anything very interesting, except if we only execute this code, it gives us the data we had before and it tells I created two groups by the two values of airbag. But you can combine it with the summarize. I just copy paste this code, put it here, and remove the first argument. After the pipe symbol, the first argument becomes this. If I do that, if I run this code, this is the same summary we did for the whole dataset, I get this. A data frame which has different rows for each of the groupings that I have. And in each row, I have the summary statistics divided by each condition. Imagine that you have, I don't know, a data set with the demographic of participants in 3 different experimental conditions. You can easily compute the mean age, the standard deviation of the age, etc., etc., the proportion of males and females, etc., separately by condition. Or, for example, you have different conditions, you have the reaction times in each condition. You can, using grouping and summarize, you can achieve, create a new data set with the average reaction time by conditions. For example, let's do that with the ANT data. You can, or let me see. No, you have to do that. So this is an exercise for you. Using the ANT data, I ask you to create a new data set, ANT SMM, so summary of ANT, that includes a new variable called mean reaction time, MRT, which is the mean reaction times, and mean error, the average error rate. And I want those summaries separately by each subject and block. So for each subject and each block, I want the mean reaction time, the mean error. So a suggestion in group I, if you have different grouping condition, before we had only the presence of airbag, if you have different grouping condition, you just add them in sequence separated by a comma. So try it out, and in a moment comes the solution. So here is the solution. Let's redo it together. So exercise about group summaries. To create a new variable or new data set called ANT summary, and we first take group by of the ANT data. By subject is called subnum here, and block is called just block. If I run this, I don't get much. I just underline the code that I want to run, and then I run only the portion of code. I get the same data back, and it tells me that I have 120 groups defined by the subjects and the blocks. I use the pipe command, and I ask a summary, and I want mean reaction time is mean of reaction time, and the other summary was the proportion of error. So mean error is mean error. If I do this, I get because the variable, I get an error because the variable was called error, not error. I get that the summary is saved into a new data frame called ANT-SMM. I can either print it down here, I can go in my environment tab and visualize it here. I get that for each subject I get 6 blocks, and I get for each subject and each block the average reaction time and error rate here. So this is very convenient when you have complex data structures and you want to aggregate those data using summary statistics. It could be also, of course, if you can put, I don't know, also the standard deviation, the median, etc., etc., etc. Now, you can compute new variables using Dplyr. How can you do that? Well, you can use mutate, which is a command that is specifically designed to compute new variables. For example, in the cars data, you can create a new variable called space, just not very meaningful, but it's just the sum of the baggage size and the tank size. And the output is a new data set that includes the new variable. So let's try to do that together. Create new variables. So let's do it. Mutate cars, and create a new variable called space, which is just the summary of the sum of, let's close this, the sum of baggage size, and tank size. Bag plus tank. That's it. If I just run this, nothing is created here. I can create a new data set called cars2, cars2. And now I can inspect it because I saved to a new object, cars2, and I get a new variable called space, which is thus the sum of the baggage size and the tank size. So in this case, it will be about 80 plus 17, it's about 97, the result. And the same for all the cars. That's also very convenient. For example, in some occasion, you want to create new variables that are combination of existing variables. One thing that happens sometimes to those who do research in neuroscience, for example, or behavioral psychology, they combine error rates and accuracies as in what is called the inverse efficiency score. The inverse efficiency score is just the reaction time divided by 1 minus the error rate. So you created the INT summary dataset before, just above. Let's take it and compute a new variable, which is the inverse efficiency score for each participant in each block. Try it yourself, and then we check the solution together. So the solution is this. You take the INT summary dataset and you pipe it into a mutate command in which you define a new variable, the inverse efficiency score, as simply the mean reaction time divided by 1 minus the error rate. Also, you can also start from scratch, and instead of using the INT summary data, you redo the grouping by of INT, you pipe it to the summarize, you pipe the result into mutate. So you see that with the pipe command, you can keep adding operation on the data one after the other. That's, you're doing many things with 3 lines of code, but I think this coding is quite clear, readable. You see the first operation is grouping, the second operation is summarizing, the third operation is mutating. Now, we can check with what we learned so far. It's not difficult to do many things, like, for example, computing scale scores. You have a data set, you collected some items that are part of a scale. In this case, for example, borderline personality disorder scale, and you want to compute a scale score by averaging those items. Well, I ask you now to upload in R the BPD dataset, bpd.csv, and this dataset includes a questionnaire that I made up. It's items between BPD1, BPD2, etc. They're called, and they should assess borderline personality disorder. Higher scores correspond to higher borderline personality disorder in general, except for the items that are marked by _R, which are reverse scored. So I want you to load the data BPD and then create a mean score for a scale, including the items from BPD1 to BPD6. So BPD1, BPD2, BPD3, 4, 5, 6, and call it BPD score. So let's check the solution together. So first thing first, let's import the data. So let's go here. I typically import all the dataset that I need in a script above after loading the page. So you go to import dataset, reader, you check for your data, BPD data, you do open, it's imported nicely, so you copy paste the code, you paste it here, you remove the call to reader, which is already loaded here, you remove the call to view, and you load the data. Okay, so now you have the BPD data, you can inspect them. So these are fake data that I created. You have this participant, sex, the age, school, the IAT scores, questionnaire scores, behavioral scores. You have this questionnaire, BPD 1, 2, 3, 4, 5. These are items of the BPD questionnaire. You see that some of them, like BPD 7R, are reverse coded. You have the full score of this BPD questionnaire. These are mock scores of the symptom checklist, like somatization, phobia, psychosis, I don't remember. Then different types of psychotherapy. Then the BPD after 2 years, if they had BPD after 2 years of psychotherapy. And then some variables collected before and after psychotherapy, self-worth, pre and post, after 1 month, 2 months, 3 months, and then anger, pre and post. That's it. I mean, these are simulated data, but I use those because I created this quite elaborated data set because it allowed to perform different examples on, between subject, within subject ANOVA, mixed ANOVA, factor analysis, etc., etc. So, first thing, we loaded the data. Then what we wanted to do was create a sum score of the variable, so mean score of the variable. So we can do that in different ways, and as you will see and you will learn, there are always different ways to achieve the same goal in R. The first one is you use mutate, create a new variable called BPD score by just summing the items of interest and dividing them by the number of the items. Another way is this. Using mutate, you create a new variable BPD score, which is the mean of, and here that comes the difficulty, you need a vector to include all, so you need a concatenate symbol to include all the items you want to compute the mean of. Another way is this. You can use row sum. This is the way I typically use. Using row sums, you create a new variable, BPD, $, so with the dollar symbol you create a new variable in dataset BPD. You select the variables of interest, so the variables between BPD1 and BPD6, and you give this as the input to row means. This is actually the method I use often, but this is also quite valid, so let's use this one. So create a mean score, like a scale score for BPD. So let's do this. Let's do BPD is equal to mutate of BPD. So we overwrite the original dataset. Imagine that you do some errors. It's not a problem. Like you overwrite the BPD data. I don't know. If you do this, I made an error. I don't have any more of my BPD data. They are gone. I only have this. It's not a problem. You go back. You rerun this line. You have your data back. So let's do this, mutate of BPD, and then we want the BPD scale. What is that? Is the mean of concatenate symbol, the variables BPD1, BPD2, BPD3, BPD4, BPD5, and BPD6. If we run this and we check our data, at the end of it, we have the BPD scale score. Aha, that actually doesn't work. I'm sorry. Sorry, guys. Just realized that this method, this one doesn't work. Let's stick to this one. Okay. For some reason, that thing is not correct. So let's use this other method. So we take the BPD score, they create a new variable with a dollar symbol, we select the variables of interest, and we take the mean value of them. That one creates the correct BPD score here. Oh, no, sorry, okay, that was my mistake. I did some confusion here. So apologies for the mistake. The point is, when you visualize the dataset, by default, it lets you see the first 50 columns. So I went here, I saw BPD scale, I took it for the BPD score, which is not. I need to ask R to visualize the subsequent columns, and here I see the BPD score variable. So this method works actually. Okay, this one works. If I go here, go to the last column, the column is actually what I expected it to be. And for example, let's go here. I can also use this other method, just copy paste the code for a moment, and the result is essentially the same. So they both work, everything works fine. So these methods are all equally valid. Now we have an item BPD7 underscore 7 underscore R that is reverse coded, meaning that, well, typical items go between 1 and 7. This one and 7 means more borderline personality disorder. This item is quite special because the higher values mean I'm sorry, the items go from 1 to 6. 6 is the maximum value, and this item here actually also goes from 1 to 6, but higher value, so 6, means psychological health, and lower value mean, for example, pathology, higher BPD pathology. And you want to include that in the scale score as well. What you do? Well, you first want to reverse code the item. So create a new variable, bpd7 without the underscore, such that its values, smaller values of BPD indicate less pathology and higher value indicate more pathology. To do that, it's just sufficient to compute the sum of the maximum and the minimum of the scale. So in this case, it will be 1 plus 6 is 7, and subtract the participant scores from 7. You can use mutate to create a new variable, and then you want to again use mutate and create the scale, recompute the scale, this time also including the BPD7 items. And here comes the solution. So, there's no solution in the slides, but we can do that together. So, reverse code items, we can do this. In BPD, we first use mutate, create a new item, BPD7, which is just equal to 7 minus BPD7R. If we do this and we go at the end of the file here, we need again to click this button to see the last columns. We have this new variable which is BPD7, which is just the reverse coded version of BPD7R. Then we can just copy paste this code here and include also BPD7. And here we get that the new scale also includes the reverse coded item. Again, I need to press this button here to view the last columns of the file. The BPD score here it is. It includes the also this item in the sum score, the mean score. Now, another similar issue that sometimes happens is that you need to transform variables. Imagine that you performed a task that includes reaction times, and sometimes you want to take the logarithm of those reaction times. The logarithm is just the most widespread transformation for reaction times. It's not necessarily the best one, but this code that I'm about to show you holds for each kind of transformation. So you want to take the logarithm, the exponentiation, everything, the square root. Well, you should be able to do that yourself actually. So I want you to take the A and T data and create a new variable called the log reaction time variable, which is just the logarithm of reaction times. The function for the logarithm, the natural logarithm, is just log. So log of some numbers gives you back the logarithm of those numbers. Try to create a new transform variable yourself, and we will see the solution in a moment. So here is the solution. It's very easy. You take the A and T data and you overwrite it. In this case, again, we are overwriting the old dataset. You can also create a new dataset with a different name, and the new variable is log reaction time equal to the logarithm of the reaction times. So very easy, let's say. Okay, something that requires a new learning a new function is collapsing variables into fewer categories. What does this mean? Imagine that you want to create a new variable that tells us if the reaction time in a certain trial are fast, or medium, or slow. Well, we want to drop all the information about the specific reaction time and only divide it in three classes: fast, medium, and slow. Well, let's do this. If we run the code quantile of A&T dollar reaction time, we get the quartiles. So the lowest limit, the minimum of the reaction time is this one. Then the first quartile, the 25th percentile. Then we have the median, the third quartile, and then the maximum. And well, that is quite. I mean, we can use that to define different classes of reaction times. So we arbitrarily define that as fast, all reaction times smaller than the 25th quantile, and medium, all the reaction time between the 25th and the 75th percent quantile, and slow, all the reaction times longer than the 75th percentile. How can we do that? Well, the function cut allows collapsing variables into categories. So, how can we do that? How can we use it? Well, first you can inspect the help function of cut to check for our options. It will tell you that, let me see, question mark cut, and we open the help file, convert numeric to factor, cut divides the range of x into intervals and code the values of x according to which interval they fall. The leftmost interval corresponds to level 1, the next leftmost to level 2, and so on. There are a couple of tricks to use cut that I want to teach. Well, the first argument is a numeric vector. So let's do cut, int $reaction time. Well, first let's compute the quantiles. So quantile int $reaction time gives us all the quantiles. Then the breaks is either a numeric vector or two or more unique cut points or a single number, greater than or equal to 2, giving the number of intervals in which x is to be cut. But then let's use the quantiles that we selected. So we need to define the breaks. It's a numeric vector, so let's create a vector. One thing that you need to know is that when you create this vector, everything works smoothly if you put the lowest limit as minus infinite, then the first cut point, which is this, second cut point is 75th percentile, and then infinite. So in this way, you take all the values between minus infinite and this number. You can also put 0 since these are reaction times, but then all the values included between minus infinite and this number get into the same category. All the values between these two numbers go into the same category, and all the values between this number and infinite go to another category. Then another trick is if you run this, you achieve your goal, but then you get these weird names for the intervals for your categories. I don't like those. This is actually an ordered factor, so a factor that tells you specifically which is the interval in which the values are included. But what you want to do often is labels equal to false. Label equal to false tells whether the levels of a resulting category are constructed using the interval notation. If label equal to false, simple integral code are returned instead of a factor. So you get this. First, second, third, 1, 2, 3 are the three categories. So 1 is the faster reaction times, 2 is the slower, and 3 is very slow reaction times. If you want, okay. You can also do that into mutate. So this actually, I took the variable out of the data frame. I can also do int equal to mutate, and the new variable was to be called RT categories. So RT categories is equal to cut of, I don't need the call to int anymore, cut of reaction times with these breaks and these labels, and I close the parenthesis for mutate. If I run this code, I get an error because I forgot to put the data frame here, int, before. One trick, sometimes your code gets unindented. If you select your code and press Ctrl I, you indent it again better. So you want to select the code and press Ctrl the letter I, like this. And it re-indents your code in a way that is more understandable. So if I underline the code and press Ctrl I get this. If I run this code and I go to here, my environment, the int, here I get RT categories. So whether the reaction time was slow, fast, medium, or slow. And this is how you get categories. Now, creating dummy variables, so dichotomous variables from a continuous variable, is just the same, except that you need only 3 breakpoints: minus infinite, the cutting point, and infinite. For example, try creating a new variable in the ANT dataset called RT_dummy, which separates reaction times that are larger and smaller than the median, which is about 405 milliseconds. You should be able to figure it out yourself. You just need 3 cut points: minus infinite, this one, and plus infinite. I will give you the solution in a second. And there it is. So you essentially, let's go to the script. Create, so this one was create categories, and this one is dummy variables. Create categorical variable from continuous ones, and then dummy variables. For dummy variables, you just change the name of the output, so RT_dummy, and the breaks are minus infinite and infinite are the first and the last point, and then let's check again, the median is 405, about 405 milliseconds. So let's plug in the exact number, and then I select everything to control I so that it gets better indented here. And if I go here, in the last column, I see RT_dummy. So if it was below the median or above the median. Awesome. So, I also wanted to tell you about outlier detection a little bit, because outlier detection is an extremely complex topic and it will require several lessons. So I suggest you this resource is a modern statistic for research and behavioral science, a practical introduction, in which Randy Wilcox discusses several techniques and provides also R code for detecting outliers. We will only focus on a simple but effective strategy, which is the box plot. Why the box plot? The box plot, what is the box plot? You probably have seen that many times. It's a box and whisker plot in which the one line represents the median. I took this picture right from Wikipedia. A line represents the median. A box represents the range between the first and the third quartile. And then the whiskers represent the first quartile minus the interquartile range, so the range between the first and the third quartile, multiplied by 1.5. And this is the third quartile plus 1.5 multiplied by the interquartile range. So essentially, everything that is below here or above here, it can sometimes be considered an outlier. But be advised, outlier, the meaning of outlier, the best definition of outlier that I know of is an observation that does not come from your population. It's not representative of your population. If you have many observations, even though you have a normally distributed variable, you naturally will have some observations which are outside of this range. Don't exclude them automatically or without thinking about it. If you really want to exclude it, don't use methods such as the mean plus or minus 2 standard deviation or the 1 standard deviation or anything like that, because that method suffers from a thing called masking. So if you have a very large observation, for example, that very large observation will quickly increase the standard deviation, thus making other extreme observation invisible to your outlier detection method. This is something that does not characterize the box plot. But really think it twice before you remove outliers. They only remove observation not because they are somehow outside the typical range of your variation, but because you have good reasons to believe that they are not interesting in your analysis. Well, so we want to draw a box plot and select only observation in ANT whose reaction times are within this range. So if we do that, it's easy. We create a new variable and we assign value boxplot of ANT $RT, so the reaction times. The function for the boxplot is simply, let's go here, boxplot of ANT $reaction time. Sometimes it gives you that error because you don't have enough space for the plot. Here, we can see the plot. This is the box plot. So we have the median value, the box and the whiskers, and then the dots here are the extreme observations. These values are probably simulated from a normal distribution, so they are probably not problematic in terms of outliers. So these are not real outliers. But still, when you have reaction time tasks, instead, the real reaction time often are not normally distributed, and they include very extreme observation. For example, because the participant got distracted by his phone and he waited, I don't know, 10 seconds, 100 seconds, he went to the bathroom and he came back 3 minutes later, and you have sometimes extreme reaction times that are clearly visible here. If you assign the output of this function to a variable, you can see that the variable is actually a list with many elements in it. Stats are the statistics. So the stats here are the lower whisker, the first quartile, the median, this one, the third quartile, and then the upper whisker. So if you want to select in your data only variables that fall within this range, and only observations that fall within this range, you can apply your node. So outlier detection is not a simple topic and it will require several lessons, but I suggest you this book, and I always focus on a simple but quite effective strategy, which is the box plot. Box plot is just a plot. You may have seen it many times. This figure, I took it from Wikipedia. It represents the median, the first and the third quartiles. The difference between this quartile and this quartile is the interquartile range, and the whiskers mark the first quartile minus 1.5 times the interquartile range, and the third quartiles plus 1.5 times the interquartile range. So what's outside the whisker can be considered as extreme observation. Consider also that, first, this method is better than mean plus or minus 2 standard deviation, because the mean plus minus standard deviation suffers from masking, meaning that if you have extreme observation, they quickly increase the estimate of the standard deviation, because the standard deviation is not a normal statistic, and what you get, and also may increase if you are very extremely mean, and that may lead to masking the presence of other extreme observations. Whereas the quantiles are robust to the presence of very extreme observations. So even if you have the greatest observation here is 10 hours, you won't get masking, you won't get other outliers like 2 minutes reaction time, for example, masked. Okay, so you can easily estimate the box plot in R using the function boxplot. So boxplot of ANT $reaction times, and you get this plot here. If you assign this to a variable, you get and you print it out, you get a list. What you want is look at the stats. So box $stats, and these are numbers corresponding to the lowest whisker, the lower bound of the box, so the first quartile, the median, the third quartile, and the upper whisker. And you may want to define as outliers observations that fall outside the first and the last of these statistics. And, well, the best definition I know of outlier, however, is an observation that is not from your population of interest. You have to know that automatically excluding outliers is not a good idea. So you have to really think it through. Why? If you have, like in this dataset, 5,000 observations, even though having an observation that is smaller than this value or larger than this value is not very likely, still has some non-null probability, even though your observations are normally distributed. So, those observations, these are simulated data that are marked as outliers, are actually not outliers, are extreme observations that are expected from your data. You don't want to exclude those. But imagine that these are legitimate outliers and you want to exclude them from your dataset. You should be able to do that. I ask you to filter out from ANT data all observation associated to a reaction time that is slower than this number and larger than this number. Try it out and then check the solution. Here comes the solution. So you just use the common filter and then keep only reaction time larger than this value or smaller than this value. And that's it. You probably figured it out easily by now. Now comes a slightly more difficult topic, which is the last one that I will show you in this introduction. So handling repeated measures data. Repeated measures data, as the ones in the ANT data set, are situations in which you have a unit or classes. You have units grouped into classes of observation. For example, in the ANT data, you have many reaction times and error that are all belonging to the same participant. Or in the PPD data, you have, if you remember that, you have the self-heart measured before, after the therapy, and after 1 month, once in 3 months. The anger as well. These are repeated measures. So you have that you measure the same variable anger on the same participant many times. Well, how can you handle repeated measures? And I'm not meaning here in terms of analysis, but we will see that later on, but I'm meaning in terms of representing those data. You can see, for example, that the way repeated measures are represented in the PPD data is different from the way they are represented in the ANT data. In the ANT data, we have one row by observation, so each reaction time gets its own row. We have that the subject, the variable in which the observations are clustered, is repeated many times, one for each observation. Variables that characterize the subject, for example, this subject was in the treatment group and was always in the treatment group. This variable is repeated every time for each times the participant appears in this dataset. Subject 1 is always in the treatment condition, and we see subject 1 is always in the treatment condition. And then you have that other variables change trial by trial, and they take different values, which is different from what happens here. I have that the dependent variable over time is represented by different variables. So for example, the anger before and after the manipulation, the therapy is made up by 2 variables. Another variables represent the anger after 1 month, another variable represents the anger after 2 months. That's different. Those 2 data formats are called the wide format, 1 row by subject and as many columns as repeated measures, and the long format, so many rows by subject, but 1 column for each variable of interest. This long format is the format that is, so this one, the wide format is most used, for example, in SPSS. But this long format is the one that is most used in R, and often is the most convenient format because it allows you to represent richer information. So, imagine that you want to go transform the data. And I will teach you how to transfer the data from the wide format to long format, and then from long format to wide format. To do this, you can use the function melt. The function melt is in the package reshape2. Melt works like this. You have, well, you call the function melt, you give it your data as input to the data argument. Then you can define some ID variables. What are ID variables? Are variables that stay the same for each participant. So, like the gender of the participants, the ID of the participant, etc. Then you have measured variables that are the variables that change over time. Like, for example, the anger before and after the manipulation, and after 1 month, 2 months, etc. Then you can give a variable, a name to the variable that will represent the different conditions. So, for example, the variable in which you will code pre, post, time 1, time 2, time 3. You can call it condition. And the value name is the name of the variable that encodes the value. So, okay, this tells you essentially the definition of each argument. It's easier probably to use melt than to explain it or to in theory. For example, let's try to use melt for melting, creating a data set that includes the ID, the sex and the age of a participant, and then the self-heart before, after the manipulation, after 1, 2, and 3 months. If you want to do that, we need to select the relevant variables. We pipe them into melt. We select the ID variables, which are ID, sex, and age. And, well, the measured variables are assumed that are all the remaining variables. So all the ones that are not specified in here. Alternatively, you can specify all the measured variables, and R will assume that the remaining ones are ID variables. And we say that the values of self-heart will have to go in a variable called score. Let's do that. So let's go here. First thing first, we need to let's comment it out. Let's comment out what you're doing, and then we need to load the package called reshape2. Now we run this line of code, and reshape2 is loaded. So let's first select the variables, the relevant variables in BPD. That will be the ID. I think they are sex, age, and then the variables that go from self-heart pre to self-heart 3 months. So self-heart pre to self-heart 3 months. Is it written like this? 3 months. It should be correct. Now we pipe into melt, but we need to tell that the ID variables are the ID, sex, and age. And is there anyone else? Yes, we want to tell that the value name variable will be called score. If we run this, we get as output a data frame. I haven't set it to any object. I can call it BPD2. And I can inspect its content here. So now I get self-heart pre, so the pre-observation of self-heart for all participants, and the score is in a separate column. You see, then I again, after all instances of the self-heart pre, I should get the first of the self-heart 1 month. Oh, that's long. Come on. Okay, I get the same subject, self-heart 1 month. I can also reorganize the data visually here by including, ordering them by ID. So I see many lines for the same subject and different observations for different lines for each observation of the dependent variable, and a column for the dependent variable here. That's it. Now, a small exercise for you. You can try to do the same with the anger variable. So anger before and after the therapy. And create a dataset in log format that you, with this information, and you can call it bpd_log. In a moment comes the solution. So here it is. You can just essentially copy paste this code, create a dataset called bpd_long. Instead of selecting self-harm, you select anger, and then you run. And then you get bpd_long, in which you get the anger. You can also sort it by ID. You get the anger and different as a dependent variable, and different conditions as different rows. Now, what if you have now a long format dataset and you want to convert it to wide format? Well, the name of the function that you want to use, Dplyr shape2, is dcast. So dcast is a little more complicated than math, let's say. What you want to do is, well, the first argument is the data. The second argument is called formula, is a formula. We will see more of a formula syntax when you will do mixed models or regression models, for example. You have the variables like the ID, age, gender that characterize the subject, are summed up at the beginning of the formula. I will show you in a moment what I mean. Then you have the tilde symbol, and then you want here the variable that defines different columns. The last one is var, is the variable of interest for like the dependent variable. So to understand it better, let's take, for example, let's see, okay, bpd_long. Let's take, for example, bpd_long. The data is, of course, bpd_long. The formula here, you should include all the variables that define the subject. So the ID, the sex, and the age. So let's write it together. Dcast from long to wide. So let's call it bpd_wide is equal to dcast of bpd_long. Now, the formula is equal to a sum of the variables that define the subject. So we'll say the ID, which certainly defines the subject, the sex also, the age also. If you have more the subject defining variables, you put them here. Then you need the tilde symbol. The tilde symbol, you can, on most computers, when you have a numeric pad, you can achieve it with Alt key, keep it pressed, and then 1 to 6. If you keep Alt key pressed and then 1 to 6, you get the tilde symbol. Or if you don't have it on your keyboard, or some computers have it directly on the keyboard, or Google it and maybe copy paste it from Google results. You ask, for example, for tilde in Google, because not on all computers can be problematic sometimes. So you take the tilde here, for example, from Wikipedia, you copy it and you paste it, and you get the same. Then, after the sum and the tilde, you want the variable that define condition. In this case, we call it variable. The last thing that you want to include is the variable that defines, let's make it bigger, you want the variable that defines the scores, which in this case is score. So value var is smaller. If you do that, okay, it is complaining only because I made the plotting area too small. If you run it, and you go to here, you check BPD wide, you see the data set in the wide format. So the this, XH, and the Angular is now rearranged in the wide format. Okay. Here is also the slide. Now the last exercise, I want you to convert the BPD wide data set that we just achieved, we just calculated, to long format. Call it BPD long 2. Then again, I want to convert the BPD long 2 to the dataset in the wide format. So I want to take the data that we have now in wide format in BPD wide, melt it in BPD long 2, and then reconvert it to wide format. I call it BPD wide 2. And in a moment comes the solution. So the solution, of course, is applying melt to BPD long 2, signaling the ID variables of interest and giving a name to the dependent variable, and then again taking the output, using dcast on it, and repeating essentially the code that we have just seen. And that will be all for this basic introduction to R, and let's see you soon for the for more advanced stuff in R. Thank you very much for your attention. I know that this probably was lots of materials, very difficult, but you don't, I mean, there is no need to memorize everything if you are a beginner now. I just want you to give an overview of many things that you can do with R, and we will probably help you to do that when we will meet again for more advanced stuff. So let's see you soon. Thank you for your